now that we've talked a little bit about units of measurement, let's talk about the numerical aspect of things, in particular scientific notation. What we'll do in chemistry is typically deal in the very small and the very large, so it's important that we have an idea of just how small these atoms are and just how many of them there are in a typical sample. Those measurements will require scientific notation to be manageable. So scientific notation, hopefully you have a scientific calculator. If you're on a computer, you certainly should have an app that allows you to do scientific notation. And it's just a convenient way of using exponentials to represent those very small and very large numbers we'll need to talk about throughout the course. So of course, I've already said it a couple of times, it's used to write very large or very small numbers, and because the atoms are very small, if we're dealing with dimensions, we'll need to go into the very small numbers, but in order to have enough atoms to do something visible at the macro scale, we'll need to have a very large number of them. So we'll deal in both the large and the small numbers here in the course. If we're looking at a human hair, human hair does vary in thickness based on ethnicity, ethnic background. So people from very far northern European descent will have slightly thinner hair, and people from African descent will have slightly thicker hair. But again, the average width of a human hair could be given as 0.000008 meters, or we could write it much more conveniently as 8 times 10 to the minus 6 meters. So hopefully right there, and again, that's just 5 zeros after the decimal point. We would get into the realm of 20-some zeros before or after a decimal point, and that could get unwieldy. So 8 times 10 to the minus 6 meters, scientific notation has saved us. It's made things much more easily accessible. Again, a large number, instead of a negative exponent like we saw with the human hair, where we had to move the decimal places 6 places to the right, so therefore 10 to the negative 6. Here, if we look at 100,000 hairs, we would write that as 1 times 10 to the 5th, because we'd be moving the decimal place 5 spaces to the left. So if we're moving the decimal point to the left before we hit our non-zero number, that will give us a positive exponent because we're dealing with a large number. If we're moving our decimal point to the right of the decimal to hit our first non-zero digit, then we'll end up with a very small number and we'll have a negative exponential. Hopefully you've all had scientific notation training. I would imagine in probably middle school or high school you should have seen it. It may have been a while ago, and so we're doing a refresher here, but as a reminder, a number in scientific notation contains a coefficient between 1 and 10. So we would have our non-zero digit there, and if it was 10, we would really go to the 1 and then add another power. So it's really going to be 1 point something or up to 9 point something and a power of 10, and then a unit. Of course, we just talked about units in the last little segment, so don't forget a unit. It's very rare in chemistry that we have a naked number. We're not dealing with just numbers, we're dealing with numbers and units. So for numbers larger than 1, the power of 10 is positive. So 150 meters would be 1.5 times 100, so our coefficient is 1.5 times 10 to the 2. That would be the power of 10 for the 100. And then, of course, the unit of meter. In the case where we have a number smaller than 1, the power of the 10 would be a negative exponent. So if we look here at this example, we have 0.0075 liters, which would equal 7.5 times 1,000th, which is 7.5 times 0.001. So therefore our coefficient, 7.5, would be multiplied by 10 to the negative 3rd. Liters in this case. Of course, remember the unit, because typically our measurements will involve units in the course. Okay, so notice the negative 3 for the 1,000th exponential. Now here we have table 1.4 from your text, and it gives some common powers of 10. So if you look, if the number is 1, right at the middle there, that means the multiple of 10 is 0. So we wouldn't ordinarily show it in scientific notation, but it would be 1 times 10 to the 0 would equal 1. If we have a number larger than 1, say if we move up 1 to 10, now we have to take the decimal point, which we don't show, but it's right after that 0, we would have to move it one place to the left, so that would give us 1 times 10 to the positive 1. We move up again to 100. Now the decimal point, we'd have to move 2 places to the left to get it just after the 1, and therefore it's 1 times 10 to the 2. And then up to 1,000 or 10,000, we just move up by 1 power of 10. All these numbers are larger than 1, therefore their exponentials are positive. We can do the same thing down below. If we go from 1 to 0.1, now we're moving the decimal place 1 to the right, and so when we're moving to the right, however many times we move it to the right to get the decimal point after the 1 in this case, or whatever the digit is in your application, will put the exponential to a negative that many. So 0.1 would be 1 times 10 to the negative 1 because we moved the decimal place once to the right. 0.01 would be 1 times 10 to the minus 2, again moving the decimal point 2 places to the right, so on and so forth. So hopefully this helps you to get the hang of it if it's been a while since you've done scientific notation. But typically in the course, we won't show an exponential until it's either a positive 3 or a negative 3. Ordinarily, we'll stick with the raw numbers up until then. That's when it starts to become unwieldy, lots of zeros. So when it's either 10 to the positive 3 or 10 to the negative 3, that's when we really start to specify that we want numbers reported in proper scientific notation. And here, hopefully, you have a calculator that you are familiar with and that you've used the scientific notation function for before. Many calculators have either an EE or an EXP key that takes care of the times 10 to the stuff, and then you just end up putting the exponential value in there. So you might hit that key. Let's say you have 4.3 times 10 to the third. You would enter in 4.3, then hit the exponential, and then just put in positive 3. That works a lot better than trying to do the times 10 to the caret or whatever character you're using. Sometimes that can cause you to be off by a factor of 10. So be very careful to try to use the EE or EXP key and do some practice, especially before the exams, so that you know you can use your calculator effectively for scientific notation. If you need to switch between the positive and the negative exponential, you typically will have a plus-minus key somewhere on the calculator that will allow you to make the positive exponential negative. Typically it's positive by default, and then negative if you need to deal with a negative exponential for a very small number like the diameter of an atom, for instance. And here we see a couple of examples of how to put them in and what you should expect to see. If you're having trouble with your calculator, get in touch with me sooner rather than later. I don't want you to have a bad first exam score because you didn't know how to use your calculator effectively. And so here we see some other examples of some values, how they might appear in the calculator. So just be careful, make sure that you know how your calculator might display a value like 7.52 times 10 to the fourth or 5.8 times 10 to the minus 2. So for that last example, it should be 0.058, and make sure that it expresses in some sort of format that's recognizable to you on your calculator. Here's another example. The value is 0.00052, and there's probably some sort of function key you might need to express, second or third function, or just a scientific notation key, depending on how complicated or simple your calculator is. But when you hit that key, it should not only change this value into scientific notation, but it should give every result that you have as a scientific notation result. So that could be a very valuable skill. If you're not familiar with how to do that on your calculator yet, please make sure you can do so by exam 1. So if you need to go back and forth between scientific notation and regular notation, just be aware that when it's a positive exponent, a positive power of 10, you'll move the decimal point to the right for that number of places, and then you'll add the zeros in to get the value back to the normal non-scientific notation result. So In the case of 2,400 meters, we moved the decimal point 3 places to the left to get the 2.4 times 10 to the third meters. If we had 2.4 times 10 to the third meters, we would go ahead and move the decimal place 3 places to the right, add in those 2 zeros, and we can get right back to the 2,400 meter value. So here's the example now for a negative power of 10, an exponential of 10 to the minus some value. So if we have at the bottom here, we see 8.6 times 10 to the minus 4. Well, if we want to get back out of scientific notation, we would take that decimal point in between the 8 and the 6, and we would move it 4 places to the left to correlate to the minus 4. That's going to give us a total of 3 zeros. Because we moved it once to the left just to get it out before the 8, we won't have as many zeros as our value. We should have 1 less. So we'd end up with 0.00086 if we're going from scientific notation of 8.6 times 10 to the minus 4 back to the raw number. Alright, so let's take a moment now and make sure that this is working out for us, that we're understanding scientific notation. So here's a couple values here. Let's see how we do putting them into the correct scientific notation. So number 1 is 0.000000008 meters, and that would either be 8 times 10 to the positive 8 meters, 8 times 10 to the negative 8 meters, or 0.8 times 10 to the negative 7 meters. For number 2, we have 72,000 liters. So would that correspond to A, 7.2 times 10 to the 4th liters, B, 72 times 10 to the 3rd liters, or C, 7.2 times 10 to the minus 4 liters? Take a moment, pause the video if you must, and figure out your answer, and we'll look and see how you did. Alright, so for the first example, B, 8 times 10 to the negative 8 meters was the correct answer choice. Of course, because it's a number smaller than 1, we would expect a negative exponential, and because we want proper scientific notation, we can't have 0.8 as an option. It has to be a number between 1 and 10 in order to fit the description. So B was hopefully an obvious choice for you. For number 2, the same basic problems were there, right? We had to make sure, in this case, it's a large number, so we want to make sure that we had the positive exponent, and we had to make sure that it was 7.2, right? A value between 1 and 10 in the ones place. So hopefully those were very simple for you. If not, let's try again on another learning check here. Okay, so this time our learning check is seeing if we can do the opposite, if we can take a value that's in scientific notation and convert it back to how we would have seen it in regular notation. So for number 1, we have 2.0 times 10 to the minus 2 seconds. Would that correspond to A, 200 seconds, B, 0.0020 seconds, or C, 0.020 seconds? For our second example, we have 1.8 times 10 to the positive 5 grams. Would that correspond to A, 180,000 grams, B, 0.000018 grams, or C, 18,000 grams? So take a moment, if you haven't already, and pick an answer choice for each of those, and pause the video if you must. Otherwise, let's go ahead and see how you did. Alright, so let's see how you did. For number 1, 2.0 times 10 to the minus 2 seconds. The correct answer choice was C, 0.020 seconds. The minus 2 tells us we'll be moving that decimal point twice to the left in order to get 0.020, right? The first time we move it, the decimal point goes in front of the 0, and then the next time we move it, we'll need a new placeholder 0. For the second example, 1.8 times 10 to the positive 5 grams, now we're moving the decimal point 5 places to the right. So the first time we move it, we get 18 decimal point, and then when we move 4 more times, that's how we end up with those 4 placeholder zeros to get the correct value of A, 180,000 grams. Hopefully this is coming back to you if it's been a while, or is still fresh if you've been using this in a previous course. But if you are struggling and you do need help, please don't hesitate to get in touch with me. Let's take care of it sooner rather than later. You will see this sort of thing on exam 1, and we certainly don't want anyone to miss questions that could have been cleared up pretty simply just by reaching out for some help. So good luck. Hopefully this is relatively easy and familiar territory for you.